Welcome back to Python for Machine Learning. Let's discuss scikit-learn. So, as usual, this is the QR code that will point you to the website for this training and the GitHub repository that contains these slides and all the material that you would need in order to follow along: Jupyter notebooks, scripts, data, and so on. So, scikit-learn is actually an end-to-end framework, and it's rather nice to work with. It's very well designed. So you can start your data exploration using pandas and, for instance, HoloViews for visualization. Then data pre-processing, again perhaps using pandas. You can do some cleaning of data. You can deal with missing values. And you would have to do some normalization. Then you have the training of your model, the testing of your model, and finally your application. And all of that can be done using scikit-learn. So in that respect, it is indeed end-to-end. Now, scikit-learn has classic machine learning algorithms only, so no deep learning, but only the, let's say, well-known and vetted algorithms that are part of classic machine learning. As such, that is not a limitation, because it can also be used together with, for instance, keras, in order to have the data pre-processing part, so your data pipeline, in conjunction with deep learning algorithms offered by keras. So, machine learning tasks, as we mentioned, there is supervised learning, and that is regression on the one hand, predicting numerical values, and on the other hand, that's classification, so you predict categorical values, so labels. There's also unsupervised learning. There you have, for instance, clustering according to some distance measure. You can also do association mining, link prediction, data reduction, and there's also reinforcement learning. So in this part of the presentation we'll discuss a few of these techniques. To be precise, we will talk about regression, classification, and clustering. The data set we're going to use is the same throughout, and it's the World Happiness Index. So that's basically a classification, or rather a ranking, of countries according to how happy their inhabitants are. And we're using two data sets, the one for 2015 and the one for 2016. We will be using 2015 for training and 2016 for testing purposes only, so we won't touch that during the training. So, what is it based on? The happiness score for a country is based on a number of indicators, of proxies. One of them is for economic factors, and they use the GDP for that. The family situation, that is a measure of your social network, the size of your social network. Healthcare, which is represented by life expectancy. Freedom, trust, so that means essentially government corruption. Generosity, which is giving to good causes. And there is a dystopia residual, which has a technical reason of existence. So all of that is quantitative data, so those are numbers. But there's also geographical regions, for instance Western Europe or Southern Asia, things like that. And that is of course categorical data. So we have a nice mix of, on the one hand, quantitative and on the other hand categorical data. This is a visualization of the World Happiness Index by country. So dark green means happy people. That is a maximum score of 8. And if a country tends to the brownish or dark brown side, then basically its inhabitants are unhappy. And of course, if you look at this, and there shouldn't be too many surprises, Northern Europe and Western Europe are fairly happy, as is North America, Australia, New Zealand, and so on. Countries that are particularly unhappy are in a state of war typically, for instance Syria or Afghanistan. So this is a data set we have some intuition about, which is nice because that will help us to evaluate our learning outcomes and see whether they actually make sense in the real world. So we set ourselves a number of tasks, and this is the first one. So we are given a number of proxies, so economy, family, health, freedom, trust, generosity, that dystopia residual, and also the region. And what we're supposed to predict is the happiness score. So that of course would be a regression task. We try to predict a number. So let's have a look at what the data looks like, and for that reason I just loaded it into a pandas data frame to have a quick look at the data. And as you can see, we have the ranking, which is of course just a number, and then the happiness score, which is what we want to predict. And you see values that range from a minimum of 2.84 up to 59. And then we have the other indicators such as economy, family, and so on. So one of the things to note is that there are in fact no missing values. For each of the proxies we have 158 entries, so there are 158 countries represented in this data set. Another thing to note is that the maximum values of many of these indicators are not 1, and they differ quite a bit. So this is one thing which we should take care of when we are pre-processing this data in our pipeline. So as mentioned, there are no missing values because all values are non-null for the 158 countries represented here. So that's good, we don't need to deal with that. An explicit count here basically shows that indeed there is no problem with missing data. Of course, if there would be missing data, there are several ways of dealing with that. For instance, you could just leave out a country for which some data is not available. That would be the simplest approach. Another thing you can do is use an imputer, which basically will replace not a number, so basically missing values, by some value, which can be, for instance, 0, which may or may not make sense. It can also be replaced by another value, which makes sense in the domain you're working in, or you can even interpolate between neighboring values. There are several scenarios possible, but obviously there is no silver bullet. What you should use depends on what you're doing and what makes sense in the context you're working in. So of course the first thing we need to do is to extract data, and each part of machine learning pipeline will have a fit and a transform. So what we need to do first is extract columns from a pandas data frame, because the data frame actually has more columns than we are interested in for the current task. So we also need to transform the data. For instance, we need to scale the numerical features to the interval 0, 1. We need to do that because many learning algorithms actually work better or even assume that your data is normalized in that interval. We will also change the encoding for the regions, and we'll switch to a one-hot encoding, which we'll explain later on. So, the pipeline for the numerical attributes. The name of the package is scikit-learn for scikit-learn, and it has quite a number of sub-modules. For instance, the compose module contains a column transformer. The pre-processing contains a min-max scaler. And these are indeed the things which we actually want to use. So we define a list of the column names for the numerical attributes, and we just do that by taking the columns of the data frame and taking a slice that happens to accommodate all the numerical attributes. Then we define a transformer, which is a column transformer, and that takes a number of arguments. So it contains a tuple, and that is one transformation. So it is min-max in the sense that we want to do a minimum maximum scalar. So essentially we want to scale the maximum value in our column to 1, the minimum to 0. The min-max scalar is going to do that for us automatically. And we want to do that for all the numerical attributes. So we supply the list of numerical attribute names. The name of this operation is minimax, and basically we will see later that we can chain them and we can compose these pipeline components into larger full-fledged pipelines. Okay, the categorical data. Of course we need to extract, just like for the numerical data, and we want to go to a one-hot encoding. So each country has a region, like Western Europe, North America, Western Europe again for Germany, and so on. So what we want to switch to is to multiple attributes. One attribute for Western Europe, another attribute is Northern America, etc., etc. So one attribute per region, and each country will have an entry 1 when it is part of that region, and an entry 0 otherwise. Of course, there will be only one entry per line in this particular table. So Belgium is part of Western Europe. It has a 1 in the column for Western Europe for that attribute, 0 everywhere else. Canada, on the other hand, has of course 0 for Western Europe and 1 for Northern America, because that's where it's actually situated. So again, from pre-processing, we import one hot encoder and we create a region transformer. So again, it's a column transformer because we want to extract from a pandas data frame, and the name of this encoder is pipeline component, this transformer, is one hot encoder. So again, we supply a list of the regions, a list of the column names, which in this case is obviously just region, and we specify the action to be done, and that would be a one hot encoder, and the categories are automatic. So basically they are inferred from the dataset. This is no problem if there is no missing data. If there is missing data, then this approach is somewhat too naive. Okay, now of course we need to combine these two pipelines because they actually work on the same pandas data frame. So we create a new pipeline, which is a feature union pipeline. So essentially it will contain two components that work in parallel. And of course they can do that since they act on different columns in our pandas data frame, and both are column transformers. So we combine the region attribute and the numerical attribute pipelines together. So those are the names, region attribute and numerical attributes, and the transformers are given as second element of that tuple. And then we can simply run the data through our pipeline. That would be the combined pipeline. We use fit transform as a method to do that. And note, we do that on the training data. The fit transform part is quite interesting because if you remember, the pipeline components which we used are in fact the min-max scalar and the one hot encoder. The min-max scalar will take the maximum for a column, the minimum for a column, and compute the transformation such that the maximum is mapped to 1 and the minimum to 0. Now of course, If we would have a different data set, the maximum and the minimum might be different. So we actually do a fit in the sense that on this particular data set we determine the maximum and the minimum and hence define the transformation, and we will apply that without fitting later to either the testing data or production data. The same applies to the one-hot encoder, because it might be that our training set contains less attributes or even more attributes than our test data, and in that case the automatically inferred attributes would not be entirely appropriate and we would have a problem. So they are determined during the transformation, during the fit phase of that application of the pipeline, and later on the test data, on the production data, we'll only do the transformation without fitting again. Okay, the result of this is a NumPy array, and that will be our input, in this case our training data, which we'll use for our regression task. So we can start training. First thing to do is to create a learning algorithm, and in this particular case, as was mentioned before, we're going to use rich regression. So that is in the linear model module of scikit-learn, and the name of that algorithm is which. We create a new one and we set some hyperparameters. So for instance, we set alpha equal to 0.5 and the fit intercept to false. We'll discuss what they are a little bit later. Okay, so training is very straightforward. We have the training data, and we simply, for the happiness score, we simply extract it from the dataset. And then we apply the fit method with the x label, the x data and the y data in order to train our rich regression model. Okay, something is not quite appropriate here. So we're creating our y values, so our target, our labels if you want, our numerical labels. We extract those directly from the data frame. So we are not doing any pipeline for that, and that is not a good practice. So in fact, extracting our target values should be part of our pipeline, and it's not. So there are quite a number of things in this presentation which are in fact absolutely not good practice, or that are downright wrong. The reason why they're here and why they are in the presentation is to point them out, because they're common pitfalls, and if you're not aware that such pitfalls exist, you might actually stumble upon them and have trouble with it. So, prediction, very easy. Our model rich regression is trained. We just use the predict method with input values in order to get the predicted output values, in this case y rich regression. Scoring, very easy. We can score x versus y, and in this case that would give us a score of 99.84%, which is actually really good. Of course, better scoring is with cross-validation. So we take our dataset and we partition it into the CV parameter 10 parts, and we train and score repeatedly, and we use a negative mean squared error in order to determine the score of our regression algorithm. And if we look at the scores, then you see that we get these here. So in this case, lower is better, and mostly we get a score of around 0.5 with a few outliers that are a bit higher. But still, it looks quite promising. Okay, so we had this alpha value and fit intercept, and I just said, well, okay, let's not discuss them now, we'll do that later. So alpha and fit intercept are hyperparameters. So they are parameters of the algorithm which you set up in advance, and your results will, in some cases, depend on your particular choice of hyperparameters. So alpha value is a positive real number, and fit intercept will be either true or false, it's Boolean. But what is the influence of the choice of those hyperparameters? So to figure that out, there are a few options, and scikit-learn supports a number of scenarios. The one which we are going to play out here is the grid search. So we'll set up a number of values for alpha. So in this case that would be 7 values, and the 2 Boolean values. They form a 2D grid with 14 entries. So 0.005 for alpha, combined with true, combined with false. 0.001 for alpha, combined with true, combined with false, and so on. So that gives you a total of 14 combinations. And you can do the training for each of them and see how they score. So this is the grid searcher, and it will also use cross-validation in order to assess the quality. Again, tenfold cross-validation, and for the scoring we use negative mean square error again. And of course we do that using the rich regression and the grid parameters which we define. So search is again just fit, input data to output data, and then we can get the best hyperparameters, and in this particular case that would be an alpha value of 0.0005 and a fit intercept which is true. So we have used fit intercept equal to false, so true is a better choice. We originally had alpha equal to 0.5, but it's better if it's a much lower value. Okay, let's have a look. So basically the result of rich regression, that would be the yellow line, and the target is the green line, so those are the happiness scores as given by the training set. So it doesn't look too bad. If the yellow line is non-monotonic, it means that countries have been classified let's say with a higher rank or lower rank than they actually have originally. Note, green line is monotonous, yellow line is not. But as you can see, there are not too many deviations from monotonicity, so a few countries have been classified a bit higher than they actually should, a bit lower than they actually should, but nothing too bad. So this looks actually quite good. Of course, what we would actually have to do in order to ensure that we are doing the right thing is running our model on data that has not been used for the training. So that's our test data. That's the 2016 dataset, which up to this point we didn't touch. We use the same pipeline as before, but note the difference. We're only doing a transform, so no fit transform. Determining the parameters of the min-max is in fact part of the training process. So if you were to use a fit transform, we would alter that transformation, and hence we would in fact be using our testing data in sort of training context, which we really shouldn't do. Okay, so we can do prediction and we can score. That is similar as we did before, and we get a score of 99.5%, which is very good. And if we plot the test target, which is the green line, and we superimpose the yellow line, which is the result of the rich regression, we see that it's actually performing quite well. Okay, now Question is, what is going on? Yes, this is quite a good result, but a few things should strike you as a little strange. One of those things is the fact that the optimal alpha value after grid search is 0.005. 0.005. So basically, that is the lowest value which was part of our grid search. That should ring some alarms, because it actually means that since we are on the edge of our search space, it might be the search space is not large enough. Okay, but in fact, if you check what which regression does, then you will see that this alpha is a parameter which is supposed to take into account overfitting. Now, if we take a step back and look at what ridge regression is, then it's actually just linear regression with that penalization term determined by alpha. So if alpha is something that is very close to 0, then we actually just have linear regression. And that's kind of nice, because that is most likely how the happiness score has been computed from those numerical parameters in the first place. So, thinking a little bit about our model and its mathematics actually helps a lot. Next, we'll talk about classification with scikit-learn.